Hi guys, in this video we will begin our look at alpha carbonyl chemistry, also known as enol or enolate chemistry. We saw enols in Organic 1 when we were hydrating alkynes to give an enol, and then that underwent a tautomerization to give the carbonyl compound. We will see enols here again, and again we will look at our mechanism if you remember Oreo from Organic 1. Okay, the first thing we want to look at is some general information regarding acidity of the sp3 CHs adjacent to a carbonyl or nitrile group. Now this can be either directly adjacent or sort of adjacent via conjugation. First, some pKa's here. The alpha CHs, that is the CHs next to a carbonyl, the first carbon is called the alpha, the next one would be called beta, etc. But the adjacent or alpha CHs of an aldehyde or ketone have a pKa of about 20. Now in this example here, there are only alpha CHs on the right side. The so-called alpha carbon on the left side, or the first carbon, has no CH. That's the same case with this example here. Next door we have the alpha carbon has 3 methyls, and thus there are only alpha CHs on the right side. But if we look at this compound, cyclohexanone, we have alpha CHs on each side. So we have to be aware of that. Either side can have alpha CHs. Now the alpha CH of an ester is less acidic, about 25. Of course, with an ester, there's only one alpha carbon, and so you can only have alpha CHs on one side. Likewise, the alpha CHs of a nitrile compound, alpha to the cyano group, also pKa of about 25. Of course, with the cyano group, there's only one alpha carbon. That's sort of the carbon of the functional group, and there's no alpha carbon going the other way. Now, why are these two less acidic? All right. First off, why are aldehydes and ketone CHs acidic? And by the way, usually it's going to be ketones that we see, because aldehydes tend to be reactive, and it's hard to do enolate chemistry with aldehydes. So I'll say aldehydes or ketones, but usually ketones are the most common here. But if we look at a ketone, I'll draw here, okay? We can have some type of base. I'll use hydroxide, and we can determine the equilibrium here. These electrons take an H, these electrons stay behind. Good old-fashioned acid-base. All right, there's one H remaining here, plus water. And this has a pKa of about 20, we said. Water is 16. Which side's favored? Actually, the weaker acid is favored. Okay, so hydroxide is not going to completely deprotonate these alpha CH here. All right, it's not going to completely form the anion, but we can form some in an equilibrium. And then maybe this can react, and that would drive this equilibrium to the right. So why is this acidic? Well, let's look at the stability of the conjugate base. It is resonance stabilized. These electrons move in here, these electrons here, and that would give Oxygen anion and double bond here. And this here is called the enolate anion. Of course, this is just one compound, one molecule here, right? This is two fake resonance structures for one hybrid. The hybrid is called the enolate anion. You can show it either way. This is your major resonance structure because the negative is on oxygen. Now, if we reprotonate here, we go back to this. But if we protonated the oxygen, and go back to a neutral compound, that would be this here, reform hydroxide. Here we see our enol, classical enol. All right. And what we just showed here is a base catalyzed tautomerization of keto to enol form. That's what we just showed here. And in Organic 1, I told you the way to remember this mechanism is Oreo. And the first O depends on if you're under acidic or basic conditions. If you're under a basic conditions, the first O stands for off. That's because in the first step here, we took H off. We took an H off, made the enolate anion. All right, but then we showed resonance. Now, resonance is not a step in real life. It's a step on our paper. But as soon as this comes off, it forms this hybrid. Okay, it's not a step in real reality. After we showed resonance on our paper, we then put the proton back on, but on the oxygen. Off, resonance, on. And Oreo can be used to remember the mechanism for any tautomerization. Any. If we're under acidic conditions, the first O would stand for on, and the last O would stand for off. Okay, why is the carbon alpha CH acidic? Because it forms a resonance stabilized enolate anion, we call it. And the charges can be delocalized to oxygen. Now it is spread over carbon and oxygen. All right. Now if we look at an ester, well, I'll make this OR. Okay. I'm going to put an oxygen on this side. I can call that carbon there, yeah. Let's consider this enolate. It's also called an enolate anion. It's not quite as specifically as the one above. But for this to be delocalized into here, right, like we did above, the problem is you have these electrons also pumping in. And because these electrons are donating towards the carbonyl by resonance, these electrons do not move in here quite as much. And so the anion is not delocalized as much as it is in a regular ketone. And so it's not stabilized as much, and the pK here is about 25. Now, if we look at a nitrile anion, which is also about 25, it is resonance stabilized, and these electrons can move here and pi bond here. It's going to be a carbon double bonded on each side, yeah. Okay. Resonance delocalization of the anion, just like above. The difference is, in the ketone we delocalize it to an oxygen, but here we delocalized it to a less electronegative nitrogen. And nitrogen doesn't handle the negative quite as well as an oxygen, and so the electrons don't move here quite as much. Overall, it's not as stable. The pKa turns out to be similar to the ester. Okay. Now, back up here, we talked about going to the enol. We need to talk about this equilibrium. Each step is an equilibrium here. And the carbonyl is actually highly favored. We'll mention that below. We mentioned that in Organic 1. Okay, we can compare the pK of these to others. Now, if that carbon is an oxygen, like this, well, that's a carboxylic acid, and the pKa is about 5. Because there, the charges are localized over 2 oxygens as opposed to carbon and oxygen. Much more acidic. Now, amides, we would expect to be in between. Charge on nitrogen and oxygen, pK of about 16 to 18. Surprisingly, they're not as acidic as you might think. I would always think that it would be somewhere halfway between 5 and 20. Maybe about 12 to 13 or so. They're not quite as acidic as that. It's more like about an alcohol or water. Even maybe a little bit less, 16 to 18 sometimes shown. But it is more acidic than the alpha CH molecule, because we are putting charge on nitrogen as opposed to carbon. Okay, so again, we're looking at alpha to the carbonyl or alpha to the nitrile. And the first thing is to understand the acidity of the CHs that are there. Okay, enolate tautomers. The keto form can be in equilibrium with the enol, all right? But the ketone form is usually highly favored at equilibrium. Okay, maybe like 99.99%. Okay, with only a very small trace amount of the enol. That's largely because the carbonyl is such a strong bonding arrangement. C double bond O compared to C double bond C. All right. Now there are some examples where this equilibrium is not as favored. Okay. And there are some examples where the enol is the favored form. But usually that's when we have something else going on, such as additional resonance and conjugation. And we will probably show an example of where an enol is favored, but usually not. Okay, this conversion, called tautomerization, can be catalyzed by acid or base. All right. Usually aqueous. All right. We showed the base here. We can show acidic catalysis. Again, we can use, remember, Oreo. And under acidic conditions, the first O stands for on. Okay, where do we want to put an H on? Well, on the oxygen. And we can essentially protonate our carbonyl. We've done that many times before. Then we do resonance. Can you do resonance of a protonated carbonyl? Yes, we can just move the electrons up to oxygen. That gives that carbocation. Now we want to take on resonance off. Take an H off. Well, this carbon only has 2 H's. We need to take one off of that carbon. All right, it has 3. Let's draw one in. Now, well, what's the minus? There's got to be a minus here. Maybe sulfuric acid or maybe HCl was the catalyst. Now the Cl minus can take that H. These electrons move here. And that will give that, and we reform our HCl catalyst. So proton on, resonance, and off. Each step is in equilibrium. Of course, that's not an equilibrium, right? No, absolutely not. That's resonance. In real life, this is just 2 steps. Proton on, proton off. All right. Proton on gives this hybrid. Proton off gives the enol. All right. Need to be able to recognize tautomers. Which of the following are enol tautomers of the compounds shown in the box? Well, what's the definition of tautomer? All right. Should know that from Organic 1. All right. And I will let you remember this and answer that question. And also here, how many enol tautomers are possible for the following compounds? Show them. How many additional CH tautomers are possible? In Organic 1, we talked about OH tautomers. Okay, this can be called an OH tautomer. The enol is an OH tautomer because the H is now on oxygen. All right, this is a CH tautomer because the H is on carbon. But there could be other tautomers of a CH tautomer, okay? When there's multiple tautomers, there could be multiple CH tautomers, multiple OH tautomers, okay? Those are the 2 types of tautomers. So try these for homework. Basically, a review of tautomerization. Probably in our other miscellaneous handout, yes, here there are a couple of drugs that you can read about. And both of them contain stable enols. This drug here, right here, enol. Okay? This drug, enol. Now, why would these enols be stable? I think I talk about that over here. Well, here's a couple of more examples of where enols would be stable. What would be the enol of this ketone here? Well, if we showed the enol, it would be this. Well, that's phenol. And it's aromatic. Okay? tautomerization gives an aromatic. See here, this carbon is sp3, no p orbital. The enol being aromatic makes it more favored. All right. Now, of course, if you drew this, you would always consider that to be the favored structure. But it's actually an enol. All right. Another example is 1,3-dicarbonyl compounds. I think I mentioned that over here. Such as 1,3-dicarbonyl compounds. The monoenol is actually the favored form, and that can be determined by NMR. All right. If you take the NMR of this pure compound, it will actually show two structures. All right. There's no way for this to ever be one structure in solution, because it will equilibrate and give 15% of this. That is just the equilibrium. But the enol form is favored. And what's the reason here? Well, we have a nice little intramolecular hydrogen bond that can occur here by having the H on the oxygen, hydrogen bonding. So that makes this structure actually favored. All right. And I mentioned the two drugs here. If you look at these, it's also, see, this H can hydrogen bond with the carbonyl. These are really 1,3-dicarbonyl compounds, with one of them being in the enol form. Okay, hydrogen bonding. Hydrogen bonding, the H would need to be over here, of course. All right. And that, by the way, is a nice six-membered sort of pseudo ring. 1, 2, 3, 4, 5, 6. Okay, so there's some general information. Now we will move into alpha substitution reactions. All right. And the first we will look at is alpha halogenation. If we have a ketone here, we can put a halogen at the alpha position, the alpha carbon, using elemental halogen, in this case bromine. All right. Using typically acid catalyst. All right. Now, usually when we do an acid catalyst, it's a strong acid, but acetic acid could possibly be considered an acid catalyst, but we're getting into kind of gray area. I'd rather you kind of always look to have a strong acid as an acid catalyst. A lot of times this may be done in acetic acid solvent, and you add just a trace of HBr as a stronger acid. Okay. Now the first step of this mechanism is tautomerization to enol. And that would give that there. Now I'm not going to show the mechanism here again. The mechanism we already showed. All right. If you were asked to show this mechanism, you would need to show the tautomerization mechanism, okay? Now again, this is highly favored form in most cases. That doesn't mean we can't have a little bit of this. And from there, focus on the alkene. Have you ever seen an alkene react with elemental halogen? Yes, that's one of the first reactions we did in Organic 1. And at that point, the alkene can react with the electrophilic bromine. The question from organic 1 was where we're going to leave cation, left or right. In this case, it would be left, and so we would get this here plus Br minus. All right. Now in organic 1, typically we always did back bonding. All right. And we also said that this was concerted, and when we did back bonding, we got the bromonium ion. And then we said that this was not actually formed. All right. Well, in this case, what back bonds is the oxygen. And from here, these electrons can move here, and that gives, well, this is resonance. This is just plain resonance, okay? And that gives that there. And so the reason this bromine doesn't back bond is because the cation is resonance stabilized. And at this point, what happens is the bromide never attacks here. Instead, it takes the H, leaves electrons behind, and that gives our product, and we make HBr. Okay? Now, since we started with it, we'll say it was reformed. All right, catalyst. And that's the chemistry that takes place, and we end up with a bromine here plus HBr, not a dibromide. Now, if we had just made a dibromide, all right, that is the bromide added here, okay, well, that's not going to be stable, because anytime you can make a pi bond, kick off a leaving group, it's going to happen, and this would give that there, and then that bromide will just take an H. So that's how the chemistry goes, and you end up forming HBr, not a dibromide. All right, this reaction is typically done with either bromine or chlorine. It doesn't work well with iodine or with fluorine. Iodine is the reaction is not favorable. It tends to be endothermic. And with fluorine, it's just the opposite. It tends to be too reactive, too exothermic, a little bit dangerous. So here's an example using elemental chlorine, HCl catalyst, okay. Some students look at this and think the HCl is what was here. No, this reaction, okay, this reaction can actually take place with just chlorine. All right, because while we do show this typically with acid or base catalysis, it doesn't necessarily need catalysis, all right? And so there is a little bit of enol here. Now, if you don't use catalyst, the reaction will actually start a little bit slow, all right? The only difference is bromine versus chlorine, yeah? And it'll speed up as it progresses. That's because what's the byproduct here? This plus HCl. And as we start forming the HCl, it can start serving as the catalyst for the tautomerization and speed up the reaction. And that's called autocatalytic. It sort of creates its own catalyst as it proceeds. Okay? So, alpha halogenation proceeds via the enol. We have the reactive alkene, but we don't do a dihalogenation. Instead, we have resonance. Okay? And sort of several different concepts that we've learned along the way, all here together. All right? We have built our knowledge through Organic 1 and Organic 2. All right. Let's look at exhaustive halogenation of aldehydes and ketones under basic conditions. If you take this molecule here with excess chlorine and excess sodium hydroxide, we can replace each CH on the alpha position. Here there's 2. And when we replace them all, it's called exhaustive halogenation. All right. We're going to make 2 equivalents of sodium chloride, and we're also going to make something else there if we want to completely balance that. Now here we're under basic conditions. Now under basic conditions, it's not actually the enol. We could get to the enol, right, as we did here. But instead of the enol reacting, we're actually going to have the enolate react before we get to the enol. And to get that, I'm just going to show the entire mechanism. And these electrons take the H, these electrons stay behind. My pen is sort of bold pointed here, and that's going to give the enolate anion. I'm not going to show resonance. I'm not going to work towards the enol, because from here I can just react with the electrophilic halogen, and these electrons do this, and that's going to give that there. All right. Now the sodium is sitting here. Now the sodium would sit with the Cl minus, and we made sodium chloride, but you see we also are making water, and we're going to make 2 equivalents of water in this reaction, because at this point we can repeat the reaction. Let me go to a finer tip pen here. We have another CH here, and the hydroxide can take this H, leave electrons behind, we make another water, and then this can react with another equivalent of chlorine, and that's going to give the product shown, and we're also going to get another sodium chloride. And now there's no other CH remaining on this side or the other side, and the reaction will thus end there. The CHs on the beta carbon are not acidic at all. They have a pKa like about 40. Not going to deprotonate them with hydroxide. Okay. Now, so the enolate is our reactive species, the nucleophile. Now under basic conditions, okay, it's always going to be exhaustive, because you cannot just put on one chlorine. Okay? Can't stop here. Because this alpha chlorinated product is more acidic than the original. If we look at the two potential anions, that versus that, this is more stable because we've got the chlorine there. Both of them are resonance stabilized into the carbonyl, but this one has the additional stabilization of the chlorine inductively withdrawing. Makes perfect sense, right? So, while this has a pKa roughly, we can say about 20, this is less, more acidic. So the hydroxide initially deprotonates this, but once this starts forming, the hydroxide is going to be like, oh, I'm going to come over here, deprotonate this one. And you're like, no, only deprotonate the starting material. And the hydroxide is not going to listen to you. It's going to be like, no, I want to deprotonate this product that we formed 5% and start. Then we can put on another one. I like to do that better. And so you can't stop it. It's a case where the product is more reactive than the starting material. And so under basic conditions, you always want to do exhaustive halogenation. Okay? And so next one you can do for homework. Now this brings us to a chemical test called the Haloform Test, or the Haloform reaction. Well, it's the iodoform test. Let's first look at the haloform. More generally, haloform. If it's bromine, it would be called bromoform. If it's chlorine, it would be called chloroform. Iodine, iodoform. If you take a methyl ketone, we can convert it to a carboxylic acid here. Do what? Well, let's look what's going on here. The first step is exhaustive halogenation. Halogen, hydroxide, excess, and so we would get carbon with 3 halogens. All right, not 1, not 2, but 3. X being a halogen such as a chlorine or bromine or iodine. By the way, under basic condition, iodine does work well. All right. Exhaustive halogenation. But it turns out a carbon with 3 halogens will serve as a leaving group from the carbonyl. All right, and this is going to be a non-isolated intermediate. We have excess hydroxide. We're still doing step 1. The hydroxide will now add to carbonyl, electrons up, I'm just going to condense that, CX3. And so that's just good old-fashioned nucleophilic addition to carbonyl. But now this will serve as a leaving group. And now the electrons come back down and kick that off, and that will give our carboxylic acid plus the CX3 anion. And the reason this will serve as a leaving group is because those 3 halogens stabilize this carbanion enough that it will apparently leave. We could have theoretically maybe predicted that, but we don't have to theoretically predict. We know that it will leave because this happens in the lab. And the hydroxide will replace it by a nucleophilic acyl substitution mechanism. At this point, this carbanion will take this H, okay, and that will give the carboxylate anion plus HCX3. And that is your haloform. Okay? HCCl3, a lot of times it is written CHCl3, more commonly written like that, is called chloroform. It's actually a fairly common solvent, although it's a little bit toxic and not used hardly at all at the introductory level. It is a common NMR solvent, if you remember deuterated chloroform, where the H is replaced with a deuterium. Okay? If it's bromine, it's called bromoform. Okay? And this is the end of your reaction. Now we need, if we want to put the H on, we need H plus workup. All right? Of course, step 1 is under basic conditions, so we expect our acidic product to be in the basic form. Indeed it is. We have to put on the H by workup. It's actually a way to make carboxylic acids from a methyl ketone, not an ethyl. If it's an ethyl, you only put 2 halogens on, okay? Not a third. And the carbon will only leave if there are 3 halogens. Who would have thought it? And so here, that hydroxide, when we do this here, is probably adding to the carbonyl. All right? Yeah. Here, all the way through. But nothing happens. There's no leaving group. And the only thing that can happen is, well, that carbon just won't leave. We just have to kick the hydroxide back off. All right? And so you don't get any new product. And so it just that's the product that's isolated. But if the carbon has 3 halogens, that carbon will get kicked off. Haloform reaction, great way to make carboxylic acids. Okay. And if we go back and consider some aromatic chemistry, we can react this with maybe acetyl chloride and aluminum trichloride. I'll show this. That would give that right. But at this point, we can come in here with maybe chlorine and KOH, excess of both. And then with H plus workup, we would expect to get benzoic acid. Now the way we did this back during test aromatic chemistry is we often reduce this, maybe with like Clemmensen reduction, or now remember Wolff-Kishner. And that would give the deoxygenation, reduction of the benzylic carbonyl, and then we oxidize this with like KMnO4, and that did the benzylic oxidation with cleavage of a carbon. But now we have a new approach to doing that. All right, great way to make a carboxylic acid. Now this can also serve as a chemical test, and it's done with iodine. And it's thus called the iodoform test. That's because the CHI3 iodoform is a solid. All right. The others are liquids. Chloroform's a liquid. Bromoform is a liquid. All right. Now that's the byproduct here. If you do this reaction with a methyl ketone, all right, we'll get the carboxylic acid. All right. But we also will get a solid, the leaving group after it takes the H. It is a yellow solid. It's not that crystalline. It tends to be a little turbid, sometimes a bit kind of oily solid, but it is a solid. Okay, this would give you a positive test as indicated by the yellow precipitate of CHI3. Where if you react this with the excess, okay, all right. Now by the way, it doesn't indicate here, but here we're using I2 and hydroxide, right? Obviously we need iodine if we're going to do iodination. Okay, and so this would be the so-called iodoform reagent, or iodoform test. This one would give the carboxylic acid plus iodoform, where this one will just give two iodines here, like above, and you will not get the iodoform formed. Okay. Why don't we end there? We'll pick up with a couple of other miscellaneous points regarding this reaction 5. What reaction are we doing? Alpha halogenation. Okay. Couple of miscellaneous things here. We'll note at the beginning of the next video. Then we'll get into alpha alkylation, putting an alkyl group at the alpha position. So really we're going to be making a carbon-carbon bond here as opposed to a carbon-halogen bond. Alright, very important chemistry here. We'll pick up there in the next video.